So, we are here again for another expert talk, and today we are going to talk about science, inspiring science education. And we have with us Mr. Sotiriou. Mr. Sotiriou is working now, he is the head of the research department of private school here in Greece, which is called Ellinogermaniki, Agogi. But he has worked at the National Center for Scientific Research here in Athens, in the Physics Laboratory of Athens University. And I suppose he is the expert to talk to us about science, and he has organized many European projects. I don't want to say more, so I give the floor to Mr. Sotiriou, and I just want to thank him for organizing with us this expert talk. So, we are all ears to hear.
So, thank you, Irene. I hope you can hear me. Can we please check that everybody can hear me? Great. Okay, so I see there are 17 participants. I see some people from Greece, Turkey, and other countries. Okay, so my talk is going to focus on how we can introduce scientific issues and recent results from research work in the field of science to schools. I'm going to discuss also the significant role of teachers, and I can give you some examples from tools, applications, and a series of activities that can help us to bring such activities in our school classrooms. So I will move to the overview of the presentation. I'm going to present a series of recent results. As we said, usually we say that the book of the nature has not finished yet, so we have really to react to comments, questions from students when new scientific news are coming, and these are really populating the news articles the last years. The situation is completely different from let's say when I was a student, and now there are numerous articles, for example, for Higgs, for new findings about the speed of light and so on. I will describe some problems, let's say, and issues we are dealing to introduce these activities in school environments. I will discuss the role of the teachers, how we see it, and how we are trying to support teachers in the framework of, as Irene said, in the framework of large-scale European projects that are organizing a series of activities and developing communities of teachers to learn, let's say, from each other and exchange experiences. And finally, I will give you some examples of what we are doing in this field. So I proceed in the third slide. This is from a piece from a book from Umberto Eco. It's quite old, I think. Now it's 10 or more than 10 years old. The title is Turning Back the Clock. And it's, let's say, focusing on the issue that usually we are presenting a magical view of science, even in our school books. We are trying, let's say, to avoid to enter in the main issues, in the real scientific work on how difficult it is to go to some conclusions at the end, and we are presenting the results like some miraculous episodes, as Umberto Eco says. And in his conclusions, he's saying that it's really our duty especially from people from research, people who are working at the outreach departments of big organizations like CERN, big research centers, to invest significant effort to transfer these ideas to students. So the message is that in the last part of this slide, that in order to teach a no-magical view of science, we cannot expect it to come from the mass media. The scientific community itself must construct it bit by bit in the collective awareness, starting with the young, with really with the students. So focusing on such issues in our classroom is really important. I will go very fast in a series of recent scientific discoveries, news that are appearing in the media. Maybe you know that Voyager, this space probe, is traveling in space since 1975, and it has, let's say, going now beyond the limits of the solar system. This was announced back in January 2011, but still in my presentation, I don't know how they can really have access to the presentation, but I have links on my presentation, on my slides. So all these are available to the participants. They can visit the specific websites and they can represent this information to their students or to have them for their own purposes. So if you enter to the website of Voyager, you can still see real data coming from the spaceship as it is traveling in the interstellar space. And there is all the explanation of how scientists were able to find that it's really there is no any interaction anymore from the sun radiation, from the flux of the particles that the probe is receiving from one side is exactly the same as in the other, so it is in the interstellar space. So this was great news. You can use this data as they are running on the website, because there are some periods where it seems that the distance of Voyager from Earth is decreasing, and this is why Earth is rotating around the Sun faster than the speed of Voyager from the Sun. So it's sometimes the distance from Earth seems to be decreasing. So all this information is available. You can also get information about the famous golden disk that this probe is carrying, that is carrying, let's say, the murmurs of Earth, voices, pictures, and so on from all species on the planet. And there is a very interesting also information. I don't know if the participants can see the small two cycles on the bottom part of the golden disk. This is, they are trying to give to the future people, or to the aliens who are going to find this probe in the future, the information where exactly we are located, by using the wavelength of the radiation that is emitted when the electron that is rotating around the proton in hydrogen is changing spin, and this emits a radiation at the wavelength of 21 centimeters. So this is the, let's say, the reference for measuring distance in the universe. Let's say between civilizations that are based on hydrogen. So these are some ideas on how you can discuss such issues based on this information. There is a big also discussion about the Cassini mission that is making unique pictures from Saturn. Now you see at this moment that this picture was taken, we have really a solar eclipse at Cassini, because Saturn is covering the Sun is from the other side, so the rings are illuminated, and the small blue dot that you see there is Earth. Again, in my presentation, this picture is connected to a video, a YouTube video from Carl Sagan, who is presenting really a similar photo from the Voyager mission when it was taking, let's say, the most distant photo of Earth many years ago, and he is describing how small we are, and in this big universe. This is another case, the Cassini mission. Now I'm moving to another area. We are on back in 1987 at the southern hemisphere. A telescope located in Australia was really the first one that was able to make a photo of a supernova explosion. I don't know if you all are familiar with what a supernova is. Supernova is the phenomenon that, let's say, is taking place when a very big star, dies. So the mass is collapsing and causes a very big explosion. So this happened about 150,000 light years away at the Large Magellan Cloud. So in reality, this has happened. This has happened when the Neanderthals were walking on our planet, and we were able to see it back in 1987. But I'm presenting that because this is very important. Let's say the supernova remnants is something like we say if we are, let's say, in Greece or in Italy or other places where there are archaeological monuments and so on. It's like these monuments for astronomers. So by observing the remnants of supernova, 3 scientists from Berkeley had managed to demonstrate with scientific data that the universe is expanding, accelerating. So this was discovered back in 2011, and this was the reason for giving them the Nobel Prize in physics in 2011. So by observing the displacement of supernova remnants in the sky, we are able to measure the speed of the expansion of the universe. There is a very big, let's say, I would say, it's like a race between the astronomers and the high-energy physicists who is going to see closer, let's say, to the start of the universe, who is going to be the first who will be able to locate that. Astronomy can go up to, let's say, about 380,000 years after the start of the universe, and they are trying, let's say, to find, as the picture in slide 8 shows, the farthest known galaxy in the universe. This was discovered in November 2012, that it is about 700 million years old. So it is in the beginning of the universe. The age of the universe is about 40 billion years old. So on the other hand, the high energy physicists, they are installing large experimental devices like LHC at CERN, and they are trying, instead of looking to the sky and trying to see back in time, to reproduce the conditions when the universe started. And this was done with the LHC detector and previous other detectors in the States, but LHC detector was the one that really boosted this field significantly with the discovery of Higgs boson. The announcement was made in July 2012, and the Nobel Prize was given to Peter Higgs last year in December 2014. Here is the article of the New York Times that are trying to present how the universe was in the beginning, a few seconds after the creation of the Big Bang. If there are questions or comments, I'm trying to also to follow the chat below. So if you have any comments, I think with there are 25 people, so we can really try to have some interaction if you wish. There, slide 10, I'm presenting now. This is as we say, a Higgs boson candidate event from Atlas detector at CERN. You can see the 4 red lines, straight lines, that are leading the center of the detector. This is, let's say, the cross-sectional view of the detector. The protons in the tube of LHC are coming, let's say, and falling vertically from both sides to the picture, and there is the collision in the center, and we see now the outcomes of the cross-sectional view. So we can see these 4 red lines. These are muon particles. They are traveling very big distances, so we are able to locate them easily. And this is a signature. We can say that Higgs boson was created for a very, very small part of a second at the center of the detector. We are not able to locate it, but it was there, and the signature are these 4 muons. So this is a candidate. We have to collect many of such candidates in order to be sure that we are able to say we are, let's say, at the level to say that we have discovered the Higgs boson. I'm moving back to the efforts of the astronomers. The astronomers had to use alternative ways because, as we said, by using telescopes that are receiving light or radio frequencies, they were able to go up to 380,000 years after the start of the universe. So they wanted to go further closer to Big Bang. So we had to use something else because we were not able to see there. So neutrinos was a nice candidate, and there was a series of experiments that started back in 1960. Later in 1980, there was also a very interesting Greek experiment that I had the honor to be part of it many years ago at the southwest end of Peloponnese, to install a neutrino telescope at about 5,000 meters under the sea level in the Mediterranean Sea. But the most successful experiment, neutrino telescope, is located at South Pole. They are opening holes 3,000 meters deep in the ice, and they are installing their detectors in order to measure neutrinos. Neutrinos is okay. Olga Keramidais from Pylos. I have spent 4 years of my life in Pylos working in Nestor telescope, as it is called. So nice to meet you, Olga. So the idea is that by using neutrinos, we can see more far away, because the neutrinos are crossing the matter like the glass, like the light is crossing glass. It's really impossible. Nothing can stop neutrinos. It's very difficult to be absorbed. So they are penetrating everything. They can cross Earth, they can cross suns, and so on, and they can go to the other side very fast. So that means that I can see more far away. And with the neutrino telescopes, I'm trying to reconstruct their track in order to see back from where they are coming from. But from where they are coming from and why they are so important. In November 2013, astronomers strike back and they discover neutrinos that they have energy about 100 times higher than the particles that are accelerated at CERN detector. So the Science magazine publishing these very thin lines that you can see in the front page of Science magazine are the detectors that are located in the ice at the South Pole, and the different colors you see there is the light that was measured from a neutrino that crossed this detector. And this neutrino was a very high energy neutrino. It had very, very big energy that cannot be produced on our planet, and it cannot be produced in our solar system, and maybe it cannot even produced in our galaxy. So from where such neutrinos can come from? These neutrinos are coming, as we are saying, from areas, from cosmic accelerators, like this, the core of this galaxy, NGC 4261, that they believe that there is a black hole in the center. So everything that is around the black hole, suns, planets, everything that is in front of the way of a black hole will enter to, let's say, to a circular motion around the black hole. The black hole must be at the center. Again, here, this is a candidate for a black hole. We were not able up to now to say that this is a black hole. This is a candidate. So all this yellow ring is matter that it is accelerated at very high speed, very high energies, before they go to the center where the black hole is located. And we believe that these neutrinos, so high energetic neutrinos, are created in these cosmic accelerators. So with neutrino telescopes we can construct such a map, let's say, of the sky, locating such areas in the universe. Moving on, 2014 belongs to space. About 10 years ago, the European Space Agency sent to the sky Rosetta to meet a comet that it is approaching our sun, and they had really the opportunity to answer a very important question, to see if the water that comets are carrying has the same nature with the water of our oceans. So there is this theory saying that this is one of the theories that the water on Earth came from comets. So they have sent a space probe to this comet. It was accelerated through gravitational force from Earth and Mars, and it was really sent very far away, near to Jupiter, in order to follow this comet as it was approaching Earth and Sun and so on. So this probe arrived to the comet in August, and in November it released a very small robotic vehicle, Philae, that was landed for first time on the comet. The vehicle was carrying, let's say, a machine drill in order to make a hole in order to collect the data, but unfortunately let's say, it fell in the side and it was not able to perform this measurement, but still Rosetta was able to, let's say, from the evaporation and the materials that are coming out of the comet, was able to see the composition of the water that this comet is carrying, and the data shows that it has not the same composition like the water of our ocean. So this theory seems not to be the correct one. So let's go now back to what we are teaching to our schools and what is happening in our schools. I have here, this is coming from the editorial part of Science magazine some years ago, presenting really the problem of science education today in the United States, but also in Europe, saying that there is a major mismatch between the opportunity and action in most education systems today. Let's say opportunity to transfer these unique ideas to our students and try to connect it with the curriculum. Instead of that, we are asking from our students to learn different things instead of demonstrating how they can think and work in following the scientific methodology. So this issue of science was calling for action in the field. This happened almost at the same time when the Rocard report was published in Europe. The Rocard was the previous Prime Minister of France, and he set up a group, an expert group, that they worked for some years in order to come up with, let's say, not so new pedagogical approach. The inquiry is quite old, but they really insist. They also developed a policy document that was followed from many countries to introduce inquiry-based science education in science education, let's say, reform efforts in the different countries. Still, of course, this is not so, I would say, successfully implemented in most of the countries, but at least there are numerous efforts. So, slide 17 demonstrates one of these efforts. It is called Open Discovery Space. It's a very big community, a social platform that involves about 7,000 teachers from all over Europe who are organizing a series of activities also connected with science. In the specific one, there is a virtual visit of 500 junior and senior high school students from 7 different locations from Greece who have the opportunity to visit the CNS experiment at CERN. In the picture you can see the technical leader of the experiment. She is at the center of the detector, exactly the place that we have seen before, this graph with the 4 neurons. And with her mobile phone, she is transferring this picture to 500, this video to 500 students that were not able to participate in one of the CERN visits. Even if you go to CERN with your students, you will not be able to enter to the center of the detector. So this is the add-on, let's say. This is a great opportunity, and you can organize it. You can contact me, and we are organizing such kind of activities for all schools. We are organizing really national visits, so we are bringing schools from the same country, up to 10 together, in order the students also to have the opportunity to discuss with the researchers. And we have the opportunity to have researchers from the same country, so they are talking to the students in their own language, and they have the opportunity to discuss the details, to perform such a virtual visit either at CNS or at CERN or at ALICE detector. Sorry, I moved too fast. So we are organizing these e-master classes, events and virtual visits to CERN. We have made a series of efforts also to connect CERN, IceCube in South Pole, and schools in Europe and in US, in order really to present this range, as I said in the beginning, between astronomy and high-energy physics, presenting the perspectives from both sides. In one case, by simulating the process, how the universe was created, at 100 meters below the surface of Switzerland and France, or by conducting researchers at South Pole. They are spending the whole winter there, so they have enough time to talk also to students. It's very interesting for them to talk and interact with students. So we are organizing these kinds of events. So let's now come to the very important role of teachers. The phrase, this piece on slide 20 is really coming from a Rocard report. It says that teachers are key players in the renewal of science education, among other methods being part, not art, this is wrong, part of a network allows them to improve their quality of their teaching and supports their motivation. So the idea of developing networks like Irene is making with e-twinning or similar initiatives in the different countries is very important. Is very important because all this information, all this experience cannot be transferred in a seminar-like activity. So by learning one from the other, by exchanging experiences, we can become better at the end. So these efforts like e-twinning that you are implementing is really very, very strong. In 2012, Science magazine with a new special issue, again focusing on science education, is it comes back and says that although we have made so many investments at national level in US, in different member states of EU, inquiry is not being implemented effectively. And the reason, according to this editorial note, is the fact that the teachers are not really, they don't have the tools in their hands in order to do that. They don't have the freedom, really. And it's explaining the fact that in countries where teachers and schools are working more autonomous, like in Finland, then the results are becoming better and better. Is there any Finnish teacher in our group? No? Oh, okay. So I'm moving on. So these are the messages we are receiving. And here is another very interesting finding from OECD International Study TALIS, Teaching and Learning International Study 2013. So they have asked teachers about the professional development programs they have recently participated. And of course, you will see that about 70% are participating in courses, workshops, and so on. 44 they are going to seminars or conferences, and so on. But there is a very interesting finding in this study. For first time, with a percentage of about 37%. The participation in a network of teachers formed specifically for the professional development of teachers appears to be the third most important way to participate in the professional development program. And this is offering, demonstrating this idea, the idea of community building for a specific purpose, to exchange experience and increase my competence in teaching. So there is a whole process for that. It's not so simple. It includes phases. It has been analyzed. It has been studied. So we need a purpose to believe in such a process. We are asking from teachers to participate and change their practices, really. So there must be a reason behind that. It's not easy, of course. There must be always some award in this process. It can be a real award, it can be really participation to a summer school, it can be the prize of a contest and so on, or part of really of the to be part and recognized as part of the evaluation and the assessment of the teacher himself or herself. We have to provide the necessary support, of course, to provide and demonstrate that through this process the teachers are getting the necessary skills, and at the end, of course, to demonstrate some change stories, present some examples of good practice from teachers themselves who have really managed to change, and they have managed to change their practice at the end. So this is on slide 27. I'm presenting all that in a graph. So my learning experiences are at the center. By being part of a network, I can have access to documents, to lesson plans, to stories, to different tools, and so on. All these are increasing have a significant impact in my professional development. I have more people to participate. I don't have only my colleagues in the school or my friends and so on, but I have a large network of people expanding also outside my country. And overall, this brings me together with a professional community that is helping me to become a better teacher for my students. So from our side, we have identified the necessity for organizing these digital resources and tools, online labs, scaffolds, all these resources in a nice framework in order for teachers to be much more easier to find them and work with them. These are organized according to the science curriculum. The good thing with the science curriculum is that there are overlaps in all countries, so we don't have the usual problems that can be discussed in other subjects about the connections between the curriculum in different countries. The importance here is the user-generated content, because these approaches are offering teachers the opportunity to contribute their own lesson plans, their own learning activities, activities that are coming from practice, so they have a unique value. These are, of course, developed, as we said, according to commonly used educational approaches, so they are offering tools that are helping teachers to produce these materials following a specific methodology, inquiry-based learning, the 5E model, project-based learning, according to the needs and the interests of each one. All these materials and resources organized in meaningful activities, tested in real environments. This is very important, providing at the same time access to real data, to advanced infrastructures, and to high quality content. So we are providing a series of learning activities, offering tools. They are helping teachers to perform all these tasks. Here, unfortunately, slide 38, as I have, let's say, an animation there, cannot be presented in the appropriate way, but I can explain about that. We are creating offering tools. These tools are following a specific process, for example, inquiry learning or project-based learning, so teachers are able to add their content to enrich the activity with resources. There is an advanced search mechanism that is helping teachers to do that, so they have the whole scenario, the whole lesson plan ready, and then they can publish it, the lesson plan, and part of it is presented as the lesson for the students. The students have the opportunity to perform the whole lesson, to perform all the activities from the system, and by the system is collecting data. They can also answer a series of questions, and in this way is helping the teacher to make, let's say, an estimation about the profile of the class as far as the problem-solving competence of the students is concerned. So the last graph shows the profile of the class. The dark blue is the part, let's say, the number of students who are not able to solve problems. Number one, a bit lighter blue, is students who are able to solve problems. Number two are efficient problem solvers, and number three are reflective problem solvers, really, where we would like to see our students to perform best. So by implementing the inquiry scenarios, the inquiry process, we are expecting really also to demonstrate to teachers that there is of course a significant investment in time, but the benefits are very important, and to have a process to really to assess immediately this with his or her class. So we are supporting the offering process, we are supporting the access to all these digital materials. We are offering a delivery environment and also self-assessment. So this is, as I said, connected with the problem-solving competence framework from PISA. So the different questions are connected with the student performance. So I have tried to present some images, let's say, of possible futures. So, of course, this is not a detailed blueprint, of course. The idea is to invest on teachers' professionalism, on teachers' creativity, in order to use these tools to make more and more interesting things. But as we said, in all of these efforts, the role of teachers is very important. I'm closing with 2 or 3 slides about the Inspiring Science Education Summer Academy. I have also the links here. This is a common effort we are making with the European Physical Society, organizing a series of 6-day long courses where we are bringing together teachers and researchers to perform such activities, to organize scenarios, to design scenarios, and then when the teachers are going back to implement them in their classrooms. So now for 2015 we are planning to have 30 European science teachers, 20 US science teachers. This will be supported from NSF, and the event will take place in July in Marathon in Greece, supported from Inspiring Science, UNESCO, EPS, and QuackNet, which is the network of science teachers in US. That's all. Thank you.
Thank you. I have to say that it was very interesting. Even though I'm a kindergarten teacher, I have to say that I learned many things. I don't know if there are questions. I know, for example, that one of the participants, Christina, is also taking part in a competition that Inspiring Classroom is organizing, as far as I know. I don't know so if there are any questions, something that you would like to ask. You can use your microphone or can just use the chat.
Unfortunately, the project for the development of the telescope in Pylos has not continued, let's say, in order to be at a place to start measuring. So as far as I know, because I have now left this field for some years, there is a common European effort to install a neutrino telescope in the Mediterranean, but there are three locations, let's say there are three candidates. One is near Toulon in France, the other one is in Ustica, Italy, and the third one is Pylos, where the Nestor telescope was planned to be installed. So we had a lot of dust, cosmic dust, but let's say not measured by the telescope.
I would like to ask something. So, if the teachers in training visit the site, the Inspiring Science site, they can join in a community, they can find ideas that they can use in their training projects, they can find other teachers who may want to work together.
Yes, thank you for this question. This is very interesting. Let me say the Inspiring Science is really, I would say, a social platform. So everyone can organize his or her own community. It can be an e-twinning community, it can be a thematic community in e-twinning, it can be a national community, it can be a school community, because also we are supporting individual schools, let's say, to perform this kind of activities. So it's Inspiring is providing the infrastructure, and based on that you can really do whatever you like, and you have the opportunity to create your own digital, let's say, repository, digital collection of materials. There is no even, let's say, I don't know how many of the participants are familiar with the process of, let's say, adding metadata in order to characterize content to be uploaded in a repository. This is not even necessary, because you can pin resources from the web or from the portal, and you can transfer them directly to your community without adding any extra information apart from the description that you would like to give. So it has a user-friendly mechanism, I would say, to add resources and create a community in order to, for example, to create a e-twinning project or more.
Thank you. So it sounds very interesting. I don't know if there are any more questions. No? I think it was really interesting, and I suppose that we all have to go back to the site of Inspiring Science, so we have time to explore it further. Thank you very much for this extra talk.
Irene, just a moment, I think there is a question, Angela Dimitriou. What's this slide? Angela, is this one?
I think I changed it, I put it back to the one that's said.
Okay, good. Okay, thank you also for giving me this opportunity, and I really appreciate that so many people have interest quite late in the afternoon, let's say, to follow these activities. Thank you. So, thank you very much.